Okay, so in this video, we work through the material that's in section 6.2, which is concerned with the Bohr model. And the Bohr model is an attempt to reconcile what was learnt by Planck and Einstein with what was known about how atoms were structured. So, as we were talking about in the last video, the positions of the lines in the hydrogen atom's emission spectrum are predicted well by the Rydberg equation. There is just a tiny little problem. That equation was formulated to fit experimental data, and it has no theoretical foundation, and the meaning of the numbers that go in here is unclear. So Niels Bohr did something very clever. He took Rutherford's nuclear sort of planetary model of the atom, and he applied to it what he had learned from Planck and Einstein to develop a theory or to develop an equation that could explain the line spectrum of hydrogen. Now, Niels Bohr was pretty young when he did this, so he's doing sort of very, very advanced physics about fundamental things concerned with the structure of atoms and the nature of matter at a really quite young age. He may even be younger than many of these guys in this class. And he was messing with stuff that Ernest Rutherford, who was sort of the old man of physics, had been doing. In fact, Ernest Rutherford is so famous that he's on the money in New Zealand, so when they put your face on the money, you've made it. So Bohr came up with a model of the hydrogen atom based around three key ideas. He said that the hydrogen atom only has certain allowable energy levels, and he calls these stationary states, because when the atom is in one of these stationary states, it neither gains nor loses energy. It's just kind of stable. And what those states correspond to is an electron in a fixed stationary circular orbit around the nucleus. And as I alluded to previously, the atom, when it's in one of these states, doesn't lose or gain energy. So this is kind of a little odd, because when electrons move in circles, they normally radiate energy. So this is a kind of a little bit controversial. Then he went on to say that an atom changes energy when an electron moves from one stationary state to another, and how it does this is either by emitting a photon, that is losing energy, or absorbing a photon, that is gaining energy. So it kind of looks like this. This is the a description describing a pictorial description of a bunch of emissions of hydrogen. When an electron moves from a orbit or stationary state that it is further away from the nucleus down to the n equals 1 state, that's a big drop in energy, then a photon in the ultraviolet region is emitted. That corresponds to a line in the Lyman spectrum. When an electron moves from a stationary state that is further away from the nucleus to the n equals 2 level, it emits a photon that's not quite as energetic, that will now be in the visible region of the electromagnetic spectrum, and that corresponds to a line in the Balmer series. And when an electron falls from a higher energy state down to the n equals 3 level, then a photon with a little less energy is emitted, corresponding to a photon with a wavelength in the infrared is emitted, and this is a line that's in the Paschen series. So that's what Bohr said was going on, and if we wanted to go the other way, then photons would be being absorbed. So Bohr introduced a naming sort of protocol for these different levels. So these are sometimes referred to as energy levels. So we'll talk about the n equals 1 energy level, the n equals 2 energy level, or the n equals 3 energy level. And sometimes we'll talk about them as being different states, because remember the language that was originally used was stationary states, and the n equals 1 level, the lowest level, is referred to as the ground state because you can't fall any lower than the ground, and then everything that is bigger than the ground state is referred to as an excited state. Now that sometimes causes a little bit of confusion because the n equals 2 level is the first excited state, the n equals 3 level is the second excited state, and so on. So you have to be a little bit careful when they start using the terminology associated with excited states. The other thing to note here is that as we go up in energy, the states get closer and closer and closer together. So the biggest gap between levels is between n equals 1 and n equals 2, then n equals 2 to n equals 3 is a smaller spacing, and n equals 3 to n equals 4 is smaller again, and so on and so on. So eventually they get very tiny spaces between those energy levels, and they become what we call a continuum. When we go up to the n equals infinity level, the electron is no longer attached to the atom, and the atom has become what we call ionized. That electron has been knocked out of the atom. So what Bohr did was he used the rules that are concerned with how charged particles interact with one another. That's called Coulomb's law, and then he used the laws that are associated with circular motion of particles, and he devised an equation that gives you the energy of one of these levels in the hydrogen atom. And here it is. It says that the energy of an electron in one of these energy levels in the hydrogen atom is just simply equal to a constant, which is indicated with a little k here, divided by n squared, where n squared is the energy level, which is a whole positive number. Okay. So that's really it. So this K has the value of minus 2.179 by 10 to the minus 18 joules. It's often referred to as the Rydberg energy. Sometimes K is given another symbol. For example, in ALEKS, I think they give the symbol Ry for the Rydberg energy. So they'll give it that symbol, but it's the same thing. Okay, so here's an example problem. It says, what is the energy of an electron in the first excited state of the hydrogen atom? So I've put it in italics here to kind of indicate what's going on. It says the first excited state, which is code for n equals 2, because n equals 1 is the ground state. So this is fairly simple. E equals K over n squared. So that's minus 2.179 by 10 to the minus 18 over 2 squared. So the energy of this electron, and that's going to be in joules because the Rydberg energy is in joules, ends up being, for this particular problem, so I'm going to have to grab my calculator here. We've got minus 2.179 second function e to the minus 18 on 4, ends up being minus 5.45 by 10 to the minus 19 joules. Okay, so really that's it. It's not too tricky. We should be able to kind of cope with that. Now, what happens when an electron moves from one energy level to another? It absorbs or emits a photon, so we can extend the Bohr equation to take that into account. So it's just going to be the energy of the final state minus the energy of the initial state. So I've just pulled K out here as the constant out the front, and so then that just becomes 1 on n squared minus 1 on n squared, 1 on n squared final minus 1 on n squared initial. It turns out that this gives exactly the same answers as the Rydberg equation, which is really good. A little trick that you'll see that we'll need to do is that if we're asked about the ionization of an atom, that is that we want to completely remove an electron from the atom, and then we just set n squared final to be infinity squared, and hopefully you recognize that 1 on infinity squared equals 0. So here's an example of that. It says, what is the longest wavelength? So longest wavelength, we should keep in mind, corresponds to lowest energy. So it's just code for lowest energy of a photon that can ionize. So that means that the n final will be infinity. An electron from the second excited state. So that means that n initial is 3. Okay, so that's kind of that's what's going on there. So let's see what we've got going on here. So what we need to do is E equals K multiplied by 1 on infinity squared minus 1 on 3 squared. Okay, so that's going to be it. And so I'm going to put that into my calculator, K being minus 2.179 by 10 to the minus 19. 2.179 by 10 to the minus 18, sorry. Over 1 on infinity squared being 0 minus 1 on 3 squared. So that's going to be 1 on 9. So that's going to give me an energy in joules. And when I do that, put that into my calculator, I got 2.42 by 10 to the minus 19 joules. Now, that's not what is asked for. What was asked for is the wavelength. So what I've calculated here is the energy between the n equals 3 level and the n equals infinity level. So that would be the minimum energy that I would have to put into the atom to get it to the n equals infinity level. What I now need to do is recognize that the energy of the photon that needs to be absorbed would have that energy, and that energy can be related to the wavelength of that photon versus the Einstein equation. So that means that hc on E equals lambda, so I can go ahead and calculate that, 6.626 by 10 to the minus 34 times 3 by 10 to the 8, and then I'm just going to put in the number that I had before, 2.42 by 10 to the minus 19, and I'll get a wavelength. So when I do that, the wavelength that I got was 8.21 by 10 to the minus 7 meters. And if I want, I could convert that to nanometers, but I'm just going to leave it as it is. All right, so that's a fairly tricky question, and you know, it would take a considerable effort to do that, so that would be worth considerable number of points on your test or quiz. Now, Bohr was able to kind of, he wanted to do more than just look at the hydrogen atom. He wanted to look at every atom in the periodic table, and there's 118 atoms in the periodic table. And he wasn't able to extend his work to all of these atoms, but he was able to extend his work to any ion or atom that had 1 electron. So ions of this type would be things like helium plus, lithium 2 plus, beryllium 3 plus, anything that has just 1 electron. Now, if you're going to do this, you have to take into account that these ions will have more protons in their nucleus than a hydrogen atom. So you have to take into account what we call the nuclear charge, and we're going to do that via the atomic number. So what Bohr found was if you included a term of z squared into your energy formula, then this worked for these 1 electron ions as well. So our revised or more complete version of the Bohr equation includes a multiplier of the atomic number squared, and we just get the atomic number from the periodic table. So here we go. It says, what is the energy of an electron in the second excited state of a helium atom? So I have to go to the periodic table and find Z for helium, and it's pretty easy. It's 2. And then it says the second excited state, so that corresponds to N equals 3. So E equals K, the Rydberg energy, times by Z squared on N squared. And now I am good. So here we are. Let's see what we've got. So we've got 2.179 by 10 to the minus 18, that's minus there, times 2 squared, or 4 over 3 squared, and so the energy equals, and this will be in joules. It's going to be a small number. Let's see what we get here. So it ends up being 9.68 by 10 to the minus 18 joules, if I enter that into the calculator correctly. Okay, so we've extended the Bohr model out to other things that have only 1 electron. Now, Bohr kind of kept playing with the math here, and he was able to come up with a formula that gave you the radius of one of these orbits for a 1 electron atom, i.e. that's hydrogen, or a 1 electron ion, and that's going to be things like helium plus, lithium 2 plus, etc. And this is the little formula here. It says that the radius of the orbit will be n squared, that's the value of the energy level, multiplied by a naught, which is refers to the Bohr radius, which is a constant that you would always be able to look up, divided by the atomic number. So problems of these type tend to be just sort of like plug and chug. You just put the appropriate numbers into the formula for the radius, and you're going to be very fortunate in that your testing and exams this quarter will be open book, so that shouldn't cause you too much inconvenience. So let's have a look at this. It says, what is the radius of electrons of the what is the radius of electrons orbit in the first state of the helium plus, in the first excited state of the helium plus ion? So first excited state is n equals 2, and then helium plus, the reason for us being given that is because we need to recognize that Z equals 2, and then now we just kind of have to go for it. So R equals n squared times by a naught on Z, and then we just have to put it in. So n was 2, so that's 2 squared, and then a naught is 5.292 times 10 to the minus 11, and then Z is 2. So I put that into my calculator, and I get a number 1.06 times 10 to the minus 10 meters. And that's reasonable because you might recall way back from Chemistry 161, we said that atoms have a radius of around about 10 to the minus 10 meters. So that's not too bad. So that brings section 6.2 to an end, and you're ready to begin your assignments for the week. So we have a couple of things going on. We've got some ALEKS objectives, we've got a lab, and we have a quiz that needs completing. Okay, hope you found the video helpful, and good luck with everything.